Hello everyone, it's August 19th. Alright, let's do this. We've done this yesterday. Count square submatrices with all ones. How many square matrices have all ones? 10, 4, so the matrix has to be a square matrix, so it has to be the so by 1, and then size is 2 and size is 3. It is essentially the same problem as yesterday, but we turned it into 2D. We will know the ones, okay? So, and then we will get because it has to be square. I don't know. Maybe we can do a reverse style. Like it's in this case, right? We have 3 by 4. So 3 by 4. How many in total? How many in total? Can you compute really fast? Well, so 3 times 4, we have 12 with size 1, and size 2 is going to be 3 minus 1 times 4 minus 1, right? That's 2 times 3, that's 6. Size 3 will be 3 minus 2 times 4 minus 2. That's 4. No, that's 2, which is 1 and 2. So in total we have 20, right? This one we can compute. And then we have, this is a 0 and this is 0. So we want to count how many will be destroyed because of this. As long as it contains this. So, okay, so how many will contain this? But then we will probably overcount. Yeah, we'll probably overcount. Probably not. Or maybe what we can do is to find the sum. Can we find the sum? Like the sum of these 4 and the sum of these 9. Yes, we can, because there is a way to do this type of thing. It's like a, if I remember, we will sum everything and then sum to the top. So it'll be 0, 1, 2, 3. Right. And then this will be this plus this. Right. And then this will be this plus this and plus this, right? So this will be 1, and this will be plus this, so this will be 3. This will be this will be 6, 10. This will just be 1. This is 5, 12, 23. Okay, so when I go with this, I want to find how many starting from this. So once we get to a point where it doesn't work, then we can just stop, right? So size 1, boom, bad. So this one, size 1 is good. Size 2, so size 2, I need to find the sum of this. So the sum of this is equal to how do I find this? Sum of this is the sum of this 6, right? 6 is the entire thing, minus this, and plus this. So this will be 6. It's not 6, it's supposed to be 5. Okay, I think this is wrong. I think it's wrong. I think you should just do this. So 2, 3, 4. 0, 1, 2, 3. And then we'll add the top. So this will be 3. This will be 5. This will be 7. This will be 1. This will be 4. This will be 7. And this will be 10. Okay. So now this will be 5 minus 1. So this is 4. So yeah, we got this one. We got 4. And then we'll say do 3. So it will be this minus this. All right, this minus this. If we have, then we'll also minus this and then plus this. But we don't have, so we don't have to. So 3, we got 1. Here, 7 minus 3. So 7 minus 3, yeah. So we got another one, and we got another one. This is 10 minus 4. It doesn't work. Right, and then more than that doesn't work. So this 3, yes, and actually it doesn't work. Right, so this 3 will get 1. Here, 1, we got 1. And then 2 will be do this. This tells me is 4. Yes, the whole thing. Now with the minus this, right? This one minus this. Okay, so basically we go for each one, and because it's 300, right? So the most. We check length is 1, 2, 3. Length. Length. Technically, we can have at each position can go 300 times, but in reality, it's not going to happen. Because once we go beyond, yeah, so once on one side we go beyond, then that's it. Let's give this a shot. to find the sum of each square matrix starting from the top left corner. If the sum of the square matrix is equal to the square of the side, we have found one desired square. I am a little bit worried about the runtime because technically it is O(n) tripled. But we'll see. So we'll first produce, I'll just do it in the matrix. So first thing we do is matrix J shall plus equal to matrix J minus 1. Once it's done, no, so if I larger than 0, a matrix ij plus equal to matrix I minus 1j. Okay. So now that's done. Now we're gonna go res. Okay, for int s. And then we can do k. Alright, that's the largest side. So 1. Okay. So it's the same. So we will find the bottom right. Bottom right is going to be matrix I plus s minus 1, j plus s minus 1. Right? Like sides is 1, size is 1, and then actually we can do it should be equal. Right? Size 2 plus 2, yeah, so that's the bottom right. And we can say top right shall equal to it's I minus 1. So I minus 1, if it's logical to 0, then we do something, otherwise it's going to be 0. Alright, so if I minus 1 is larger or equal to 0. So we have I minus 1. Right, so we have matrix I minus 1. And now we go to the right, it's going to be j plus 1, j plus s minus 1. So top right, so bottom left, so equal to j minus 1 logic equal to 0. So it's going to be matrix j minus 1. So j minus 1. This is going to be I plus s minus 1. Right. Of course, otherwise it's going to be 0. So bottom left, so top left, j I minus 1 logic equal to 0, and j minus 1 logic equal to 0. Right. Okay. So just say if bottom right minus top right minus bottom left plus top left, if it's equal to s times s, then rest plus plus, right? But there's another thing. If I plus s minus 1 is larger or equal to n, or no, m, j plus s minus 1. Now we break. Otherwise we go through this. I think I can do res plus equal to this. Okay, let's give this a shot. Let's run this. Hopefully it does not time out. Oh, it does not time out, but it's pretty slow. I don't know. I mean, this is not the first time this type of thing happens. I'm not sure. Maybe there's a way to cache this. Like if you find a big one, then you can compute what's inside, right? So what you're saying is, if we find so we should go from just like for this, I can go, from 1. Let's say I find a big one, right? Everybody's inside. I keep going. So I go 1 is good, 2 is good, 3. So we find the largest starting from here. Okay, so this is the largest that's starting from here, and from this we can compute. Right, from the sides we can compute how many is in there. Now once I finish computing, because it's not possible to do this, which means there are some zeros in here. But yeah, this is the part where I don't know how to reconcile, because like the things inside we have computed already. So when I go to this one, let's say we have this part, but this part is already considered. How do I differentiate the two? I don't know. Whoa, we got good performance back then. Oh, this might be a good check. Yeah. Change the condition for looping through S. So basically we say S times S shall smaller or equal to matrix INJ. Nope. It's the bottom one. Shoot. Okay, it's fine, it's fine, it's fine. We'll do this. If this time this is larger than bottom right, we'll break. Let's see. Nope. That ain't it. Huh. I get a DP. dpij is the number of squares ending at. If matrix is equal to 0, yes. Otherwise, dpij shall be the minimum of dpi. So this one, and diagonal plus 1. Huh. dp. Because I am 1, right? So I say ending at here, and a minimum ending at here, and a minimum ending at here. Why? How do I turn this off? That's different. Yes, this is formed by this, this, and this. So if any one of them cannot form, then this cannot form. But if they all can form, then this can form. So to form this is depending on these, right? So if this can form, which means everybody's good. If this can form, and this can form, and this can form as well. But if any one of them has lower, let's say if this is a 1, which means you don't have everything, which means for this I cannot form everything. Oh. Yes, it depends on the existence of smaller valid ones, which means if you have a smaller, it's not valid, right? If we have something that's not valid, like, and then for you, ending at here, you will take the smallest. Yes, you'll take the smallest. Because with ending at this, what's the total number of squares, right? And then you say the total number of squares is whatever squares we have here, the smallest of them, and a plus, because this is a 1, so we have plus 1. We add a new one. Yep. Alright, I'm back. Yeah, I guess it makes sense. Ending a here requires, it's by itself and requires everyone to work and require everyone to work. If at any point some of them doesn't work, right? Some of them doesn't work, then that means, I don't know, what if this is 1? Which means we probably have a 0 somewhere, right? Then for this, I'll take the smallest. Yes, because this is still going to form, but it's on this level. It's not good. Wow. I don't know. I don't think I can figure this out. I'm all by myself. I think there's barely any improvement in my ability, because the last time I used exactly the same solution as this time. We do this quite convoluted 2D prefix sum. Yeah, this is from the tutorial. We can use dp, where dpij, right, is the number of square matrices ending at matrix ij, right? Now the relationship is dpij equal to 0 if matrix ij equals 0. Otherwise, dpij shall equal to minimum dp I minus 1j dp ij minus 1 and dp I minus 1 j minus 1, right, plus 1. I have solved this problem back in when? 2024, right? Back in October 2024. I use exactly the same, right? Exactly the same method as solution 1, and I couldn't figure out the DP solution. Today, I'm solving the same. I'm essentially repeating what I did a year ago. In other words, there have been no improvement. No improvement at all in my problem solving skill. Yeah, this is actually quite disheartening. At a certain point, I guess this is what it is. You don't improve. You literally do not improve. That's sad. Alright, anyway. Alright, so we got this. What else do I need? We'll go DP. Well, the matrix is the DP, so we'll do that. And then we'll just go through everybody. Okay, what else? Well, we have up, down, diagonal. We have 3, right? So up shall equal to I minus 1 is logical to 0. If it is, then we say matrix I minus 1 j. Right, otherwise it's 0. down. Ooh, can do this. Actually no. Up, down, diagonal. Oh, it's not down. Up and left. J minus 1. Right? And then we have diagonal. Okay, now all we need to do is we say matrix ij, okay, plus equal to minimum minimum left b, and then once we're done we say rest plus equal to matrix ij. Okay, give it a shot. I mean, we know it's gonna work. Yep. Yeah, this is gonna work. Ooh! It is not! Huh, what did I do wrong? I don't know. I have no clue what went wrong. This and this and this, right? We take the minimum of these three. And we plus, oh wait, hold a second. Yeah, this is not right. I have no idea what I did this way. Matrix ij is equal to 0. We'll continue. Yeah, my bad. This is the line. I forgot. See? You even did a wrong one. Yeah, it was my bad. I was didn't think. This looks about right. That's 1 squared. Okay, that's about it.